Hi there, this is GCSE Physics, this is Space Lesson 3, and this one's Stellar Life Cycles and Nuclear Fusion. So to start with, let's try and use bullet points to summarise how stars are formed, so that's a recap of Lesson 2. And then can you also state why stars don't collapse under gravity? Just going to pause and do that. Alright, let's move on. So, from last lesson, you get a cloud of gas, or nebula, mainly hydrogen gas. Gravity pulls it all in closer. You could expand on that a little bit. Gravity pulls it in closer, it starts to rotate and move really fast, which makes it really hot, which then leads to nuclear fusion at approximately 15 million degrees Celsius. And then the stability side of things is that the gravitational force pulling it inwards is equal to the forces from the nuclear fusion acting outwards. So therefore the star is indeed stable. Moving on. So how long do stars shine for? So approximately 10 billion years on average. That's a very average star, one like our sun. So what could affect the life cycle of a star? So bigger stars undertake fusion at a much higher rate and consume their supply of hydrogen more quickly than smaller stars. So different sized stars have different life cycles. They're also different colours. So yellow ones are average. And then as you move up, to the blue end of the spectrum, the stars get much hotter. And the life cycle of a really, really big star, the blue hypergiant, for example, might only be around 10 million years. So a big difference. But obviously they burn hotter and subsequently don't burn as long or undergo fusion for as long. Right, now this might be helpful. So a little flow diagram, if you want to sketch this out, it might take you a minute. So we'll start with nebula and then we'll work through the life cycle of stars. So the first one is a protostar. Let's write this one in. And a protostar is it's basically just protons, so it's a bunch of protons, or hydrogen, because hydrogen, remember, is 1,1. And that happens at around 1.5 million degrees Celsius. And then we're going to move into the main sequence, or the main stable period. So moving on. Main sequence star. So stars release energy as hydrogen fuses together, doing so for millions or even billions of years. This energy will be released until the star runs out of hydrogen, or its hydrogen stores start to diminish. And then what the star will do is start to fuse heavier elements together, so such as helium, and then fuse into carbon, etc. And it'll go all the way down to iron. So elements up to iron will be fused in a star as it begins to run out of energy or run out of hydrogen. So protostar leads into a main sequence star. The main sequence star is where you've got the gravitational force pulling it in equal to the nuclear fusion that's pushing back out. So let's look at a death of a star similar to our sun. So left hand side is similar to our own star. So the star runs or begins to run out of hydrogen. This is the end of its main sequence. And it begins to expand. There's a bit more to it than that. So essentially, if you think about it, the nuclear fusion that's pushing outwards will start to diminish, and gravity will win that war. And what happens is the gravity will essentially crush the star, and this happens in milliseconds. So it'll crush the star very quickly, and then obviously you've got all that energy and heat all in a much smaller volume. And then what it does, it expands outwards, and it'll expand outwards into a red giant. And what it does, it'll turn red, because obviously you've got all that energy now in a greater volume, so it'll cool down and turn red, and we call that a red giant. So red giants can be, many orders of magnitude greater in size compared to the original star. So a white dwarf, when fusion stops and no more radiation is released and the star collapses in on itself, it'll form a white dwarf, which is smaller than the original star. And eventually, it could become cold, forming a black dwarf. There are no black dwarfs in the universe at the moment. The universe is about 13.8 billion years old. And black dwarfs simply, there hasn't been enough time for white dwarfs to extinguish, all of their energy and no longer shine at all. So that could take, anything between 50 to 100 billion years before we can observe black dwarfs. And even then, it'd be quite problematic to look at it because they'll be giving off no light. So when you look for them, they'll be very, very difficult to see. All right, so what about death of a star that's bigger than the sun? So large stars, the same process that I talked about before, where the gravitational force will eventually overcome the diminishing rate of nuclear fusion. So the pressure acting outwards will be diminished, and gravity will win, contract the star, and then it'll swell up. But this time it'll be even bigger, obviously because the initial star was much bigger, and it'll become a red supergiant. That process that I talked about can happen multiple times, so expansion and contraction, and eventually it explodes into something called a supernova. So supernovas are extremely violent explosions, so it'd be like a fusion bomb, a nuclear fusion bomb, but obviously the bomb is initially the size of a star, so it ejects matter into the universe at around 40,000 kilometers per second, and the blasts, they produce much of the material in the universe, so elements such as iron and heavier than iron. So in a normal star, you get fusion up to a certain point, named up to iron, and then in a supernova, all of these heavier elements can be formed as iron and whatnot are all forced together to make even heavier elements. So stuff like gold, platinum, they're all made in the center of an exploding supernova, uranium, plutonium, and then they're ejected, across the universe. So heavy elements are only produced in supernova, and all of us carry the remnants of these distant explosions within our own bodies. So, we're basically made of exploding stars, because that's where matter comes from. Supernova add enriching elements to space clouds of dust and gas, furthering interstellar diversity, and enriching nebulas. So as we've got here, heavy elements larger than iron are formed during the explosion of a supernova. Right, so after a supernova, the core is left in a dense compact object known as a neutron star, which is composed only of neutrons. These objects are incredibly dense. A bit of trivia is that a spoonful, if you could get a teaspoonful of neutron star, it would have, the approximate mass of Mount Everest, so exceptionally dense. The object's quite small, so they're around 12 miles in diameter, and they can spin at really frightening rates. So I believe that if you imagine something that's 12 miles in diameter, and has the 1.2 solar masses, so 1.2 times the mass of our sun, for example, and it'll rotate. I think the record is about 717 rotations per second, which is pretty crazy. It's a conservation of angular momentum. So if you study physics at an high level, you might look at, and you do astrophysics, you might look at these things in more detail. Then if it's even heavier, or even more dense, if the star has enough initial mass, it'll become a black hole instead of a neutron star. And black holes are so dense that they collapse space and time, and not even light can escape. So they're just taking everything. So there's a couple of gifts. One is a rotating neutron star, and the other one, black hole. So that should be a flow diagram. So start off with nebula, protostar, main sequence, similar size to to our star, the sun, red giant, white dwarf, eventually black dwarf. Remember, black dwarfs don't exist. The other side, red giant, supernova, neutron star, and black hole. There's a couple more things which I'll show you in the next diagram. If you want to add these, you can add a planetary nebula after the red giant. So that material will be used to recycle a new solar system. Right, let's do a recap on nuclear fusion, just to make sure. So here's a typical one. So you got deuterium, tritium. So they're basically just isotopes of hydrogen. So remember, hydrogen is just one proton, one electron. Deuterium is, a neutron in there, and then tritium is two neutrons. And an example is they fuse together to make helium and a neutron, plus lots of energy. So this is just one of the nuclear fusion reactions that occurs in a star. And just to recap, so stars, normal sized stars can only fuse elements together up to iron, Fe, which is here. And elements heavier than iron are formed in a supernova explosion and then distributed across the universe. Remember that initial distribution is approximated to around 40,000 kilometers per second. So quite fast. And a common question. So remember, we are made of stardust, and how do you know that the Earth is made from the remnants of a supernova? This is a typical question. And it's the fact that elements heavier than iron are present on Earth proves that the Earth was made from the remnants or dust from a supernova. So quite a lot of new information there, but hopefully you found that useful. And now you've got a more thorough understanding of, the life cycle of stars and how elements are formed. All right, thanks for listening. I'll speak to you soon.